the scanner. Then in contrast, bottom up, as the name suggests, we start with the token list that's coming from the scanner, and then you try to apply the productions in reverse so that you end up with the start symbol. Okay, so top down, you start with the start symbol of the grammar, work your way down until you get to the leaves of the tree, which will ideally should match the token list coming from the scanner. Bottom up, start with the token list, and try to figure out what productions were applied in reverse up until we get to the start symbol. So just to review what we did last time, we said the goal of syntax analysis is to recover the structure of the program as intended by the programmer. And of course, we know that because programming languages are not regular, we cannot use regular expressions or DFAs or NFAs. So here we have to use CFGs to describe the programming language. So given a sequence of tokens, we want to look for a parse tree that generates those tokens. And this process is what we call parsing, trying to identify the parse tree. So just give me a second, I saw something. Okay, apologies for that. So we want to recover the structure of the user's program. So that's what we're referring to as parsing. So let's look at top-down parsing. We said we start with the start symbol of the grammar and try and work our way down to the token stream, figure out what productions we're applying until we come up with the user's program. So supposing this is a token list from the scanner, we have int plus bracket int plus int bracket, which by now is what your scanners should be producing. And this is our simple CFG. We have two non-terminals, E and T, with the productions as shown. So of course, the parse tree, in this case, we want to come up with something like this, that E is written as T plus E, and this T goes to int, and this is written again as a bracket E bracket, until we end up finding a matching tree as shown. So we want to look at the algorithms that we use for top-down parsing to start from this point up until when we're able to say we have a match or we don't have a match and generate an error message. So of course, there are many challenges with top-down parsing, because the first thing is that we start with virtually no information. All we know is that we're starting at the start symbol. And of course, every grammar or every program written will always start at the start symbol. Yeah, so which matches every program. So already, if a program is erroneous, we'll start by starting with the start symbol. So it's a bit dumb in that sense. Then the next question becomes, how do we know which productions to apply now from the start symbol? So in general, it's a very difficult problem because you still haven't seen the user's program when you're doing top-down parsing. You haven't looked at the tokens. Yeah. So we're just trying to guess. Yeah. So the best we can do is to guess, and then so you guess a production, check if it's gonna end up with the token stream. If not, you keep backtracking as needed. Okay, and I'm sure you've come across backtracking algorithms in other programming units, so this shouldn't be new. So now, if we want to guess, how do we do it at least intelligently? Because remember, at the end of the day, we want to ensure that the compiler code compiles pretty fast. So as much as we're doing a backtrack, we want to do it a bit more intelligently so that we don't slow down the compilation process. So top down, the one way is to think of parsing as a search, and that's why we're saying that we're doing a search where you attempt one path. If it doesn't work, you backtrack and you try the other one. So you can think of it as searching a graph search. So each node is a sentential form, which means it's made up of both terminals and non-terminals, which can be derived in a number of steps from the start symbol. Then we know that there is an edge from node alpha to node beta if and only if we have a derivation where alpha is written as beta. So at least we're saying how we are forming our tree, that you can only have a rewrite from E to T if there's a production where E is written as T. Basically, that's what this means. There's an edge from node alpha to node beta if and only if we have a corresponding rule like this production in the grammar. So let's see how we do parsing as a search. So supposing this is our grammar, we have the two non-terminals, each with two productions. So we said we always start, for top down, we start with the start symbol of the grammar. So in this case, it's E. The one that we always list first, we assume that is the start symbol of the grammar, the start non-terminal. So we say E, we have two options. You could either write it as T, or you could rewrite E as the second production, T plus E. Then for T, if we take now this path, T, you can write it as either int or bracket E bracket. Bracket E bracket can go to bracket where E is written as T or the E is written as T plus E, and you keep expanding the search space as such. If you take this as a tree or this as a branch, we have E can be written as T plus E. Then this T can be written either as T plus E, sorry, this T, then this E, we write it as int or bracketed int. So you get the picture, so that we keep asking if at any point, if I was to write these, what options do I have? I either have to write it as T plus E or I write it as T. Then you come again and ask for this T, what are my options? It could either be int or it could be bracketed E, and so on and so forth. So we are creating actually a very huge search space. So now parsing in this case will mean that you're going to try and take a path, keep going. If you find it has not matched, you're not able to proceed, you backtrack to the last place that matched and take the next branch. Okay, so I'm sure you're familiar with backtracking. Yeah, so in this case now we are searching for the path that starts from the start. We're searching our graph for a path that's starting with the start symbol E. We find a sequence of production rewrites that end up with the token string. Then now we say, aha, we have found this is the path tree. This is how we wrote E. We wrote E first as T plus E. Then we wrote this E as T, and then we wrote T as int, and then the other T as int, and we have now found that we've matched the token string. So that's what we mean by parsing as a search. So we have two top-down algorithms that we're going to look at. The first one, of course, is breadth first, in contrast to depth first search. So let's go through the breadth first search. So here we introduce what is called a work list. And basically a work list is a list of working strings that we're here to expand. So these are work list of sentential forms. And at the beginning of the algorithm, basically the work list has just the start symbol, S. Then we go through this algorithm. While the work list isn't empty, do the following. Remove an element from the work list, of course, the one that's at the top of the stack. If it matches the target string, we have found a match and we return the parse tree as discovered. Otherwise, for each possible string that can be derived in one step from the element that we removed from the work list, add that string to the work list. And you keep doing that until the work list is either empty or we have found a match. Or if it's not empty and we've not found a match, then we return an error message. Okay? So we're able to recover the parse tree by tracking the productions that we have applied at each step. So let's look at an example. Sorry. Just give me a second. Okay, so let me see this. Yeah, so I think I moved my slide in the wrong way. Yes, we were here. So we're looking at an example of the breadth as such and introducing the notion of the work list. So we have our work list. We're going to keep populating it as per our algorithm. We have our grammar symbols and we have the token stream. This is what we are trying to derive a pass tree for. So you see at the beginning, the work list basically just has the start symbol of the grammar. And give me a second. So we said the work list, we always start with a start symbol at the beginning. Then we now want to process this. So we want to look at all the options for rewriting that non-terminal based on the grammar. So E, and remember we're doing breadth first, so we're going to generate all the possible options for E. So in this case, we can rewrite E either as T and either as T plus E. Okay. Then once we do that, these don't match our token stream. So we just add them to the work list. So we add T and T plus E to the work list. And the algorithm says we continue doing this up until when there's nothing else in the work list or we have found a match. So in this case, we then now continue. We then take the top of the stack, which will be T from the work list. And then the same thing, we generate the possible options from T. And T can be written either as int or as bracketed E. So in this case, int does not match what we have, so we just add it into the work list. And the same thing we add into brackets into the work list. And then the next step, we get T plus E out. The same thing, we generate the possible options for T plus E. So this gives us T can be written as int. So here we have the int, and of course this plus E is still there. And then this T can also be written as bracketed E. So we end up with bracketed E plus E. We figure out how else, because remember we're doing a breadth as such. So this E, how would we write it? Either as T plus, we can write it as T, so we are left with T plus T. And again, we can write this E as T plus E. So we have T plus E. Okay. Then none of these match what we have. None of them match our token stream. So we add all these into the work list. Okay, so now we've added int plus E, we've added E plus E, we've added T plus T, we've added this. And then we continue. So we come and get the next at the top of the work list. We have int. So in this case, int doesn't match. So we get the next from the work list is bracketed E. There's no match because we don't have a bracket, but of course we're going to rewrite the E. So in this case, we rewrite the E with the two options, either T or T plus E. Then we add them to the work list. Hope you're getting the gist now. Then we get the next thing out, which is int plus E. So here we have one non-terminal, which is E. So we have the two options. We can rewrite it as either T or T plus E. So we generate those two options. They still don't match our token stream. Here we have int plus a non-terminal, so we add them to the work list. Then we pop the next thing, which should be the bracketed E plus E. And we keep doing that. We generate all the possible options because this is a breakfast. And then add all those into the work list. Then we get T plus T, which is at the top of the stack. We write T as, we have int plus T, bracketed E plus T plus int. Then we add those into the work list because we still don't have a match. Then we get T plus E, and we keep doing that. As you can see, it keeps generating very many options. Okay, so we're gonna keep doing that. So what do we notice, right? So you can really get the gist that we're generating very many options, but there are already some options which we know would never ever match, but our algorithm does not allow us to eliminate them. So in this case, out of the things in our work list, the ones that would possibly ever match are the ones that are in blue. There are no brackets in our token list, so anything with a bracket, we know, in fact, we should not bother with it. Again, we have only one operator. So where we have 2 plus operators, also, we know it will never match. But unfortunately, now with the breakfast, we just have to keep generating all the possibilities almost unintelligently. So this is a big challenge with the breakfast search. So as we've seen, breakfast search is slow in the sense that we use a lot of time and memory usage. So a lot of wasted effort because we've generated sentential forms that could never possibly match, like the examples I've just given. However, we know it's a bit hard to tell what can match, and that really is the whole challenge of parsing. But that doesn't mean that we just use a blind algorithm. So there's been a lot of research into how do we make the best guess of the productions that can match the user's program. And we'll be looking at improvements on BFS. So the other challenge with BFS is that it has a high branching factor because we're doing breakfast search. Every sentential form can expand. If it has a non-terminal, we're going to expand all the non-terminals. And that's why we're ending up with something like this. So we keep expanding. So you can imagine if we're continuing with this, T would generate 2 more options, then we come to T plus E. So by the time now we come here and generate int plus T, would have wasted a lot of effort. So we need a way to quickly just eliminate the sentential forms that would never possibly match our token stream and only focus that at least are promising in terms of what is the user's structure. So how do we reduce the wasted effort? So the logic goes as follows. Supposing we're trying to match some string coming from the scanner, we call it gamma. And suppose we have a sentential form we call tau, which is written as alpha omega, where alpha is a string of terminals. So we're saying we start with a string of terminals, and omega is in sentential form, so it could be a mixture of both terminals and non-terminal symbols. So what we want to do is check if alpha is not a prefix of the string we're trying to match, meaning that the front part of alpha does not match the front part of the string we're trying to match, then we know that no string derived from tau could ever match gamma, and we should not waste our time with that. Yeah. So what we want to do is if we can find a way to try and get to put the prefixes of terminals at the front of the sentential forms, then we're able to start pruning out impossible options. So in other words, what we are saying is that if we are looking at this, let me give an example like this. If you see something like this, and we're saying we want to get prefixes that are terminal symbols at the front, so that we're able now to just check. If I see this is int and int, I'm okay. If I see it's a bracket and this is an int, I know that particular production will never give me int because it's starting with a bracket. So we want to find a way where we always have terminal symbols over here so that we can quickly match them to the token stream, which is coming from the scanner. So let's look at how to do that. Yeah. So that's one idea. So we want to find a way to try to get a prefix of terminals at the front of our sentential forms so that we can eliminate the impossible options. The other thing we want to do is to reduce the branching factor, because when we do breadth first, we are branching for every non-terminal that is in the sentential form. So if a string has so many non-terminals in it, the branching factor, of course, is going to be pretty high, and actually it will be the sum of the number of productions that are involved for each non-terminal that we have. So we want to find a way also to restrict which productions we apply so that we do not have such a high branching factor. Okay. So we introduce now the notion of leftmost derivations. So we did a recap of a reminder of what leftmost derivations are, and we said a leftmost derivation is a derivation where we only rewrite the leftmost non-terminal. Okay, so we expand only the leftmost symbol first. So we're going to use this to improve the BFS that we've seen, so that we reduce the branching factor and also take advantage of ensuring that we have a prefix of terminals in our sentential forms. Okay. So by considering only the leftmost derivations in our updated algorithm, first we're going to dramatically reduce the branching factor, and then secondly, we're going to increase the likelihood that we get a prefix of terminal symbols. And once we do that, it then becomes easy to prune out sentential forms that can't possibly match, therefore avoiding the wasted effort that we have come across. So let's see an example of the updated leftmost BFS. So we're calling it updated because we're now putting a restriction that we don't just rewrite all the non-terminals for a given derivation, but we write only the leftmost non-terminal. So for the same example, we have int. So in our work list, of course, we start with the start symbol of the grammar, which will be E. So in this case, we rewrite E as our two options would be either T or T plus E. And we put that into the, we don't have any prefixes here, so we can't compare. So we put that in the work list. And note now what we're doing, because we've rewritten E, we now remove E from the work list. We replace E with the two productions that have been derived from E. I forgot to mention that. Then now we take T. Our options are T goes to int or bracketed E. So E into brackets. Okay. So what do you expect to happen here? So when we look at this, because now here we have our prefixes, we're able to check whether the prefix in the derivation matches what we have. If it doesn't, we've pruned it off. So in this case, our prefix is just giving us int. Sorry, our derivation is just giving us a terminal symbol int, whereas our token stream has int plus int plus int. So there's no way this could ever generate a plus and an int, because in fact, this is a terminal symbol. The same thing with this production. When you look at the prefix of this sentential form, it starts with a bracket. Our prefix for our tokens, there's no bracket. So none of these two would ever give us int plus int. So we prune them, which is now what the data algorithm is telling us to do. So those ones now we are not going to put them into the work list. Okay, so we've gotten rid of those two. So we just have T plus E. Now T plus E, of course, we expand it. The leftmost non-terminal will be T. So unlike breadth, where we're going to have 4 different expansions, here we're only going to expand the leftmost non-terminal. So T has 2 options. We write T as int, giving us int plus E, or T has bracketed E, which gives us bracketed E plus E. And the same thing now, what we want to do is compare what is happening. So in this case, we look at our prefix. This one gives us int plus E. So at least there's a bit that matches int plus matches, int plus matches. So this one is good. This one is starting with a bracket. Our token stream doesn't start with a bracket. So that means then we have to prune that off. That one will never lead us to the token stream that we want. So in this case, we only push int plus E into our work list. Okay. So then now when we have int plus e, again, we have the leftmost non-terminal is e. So we're going to rewrite it with two options. We'll write e either as t or e as t plus e. So it gives us int plus t plus e. Then the same thing, we come here and we match our tokens, And in this case, here we have, when you look at the front part of our working string, we have int plus, it matches our int plus. The same thing here, we have int plus, the prefix, because this is a non-terminal, so if you stop at int plus, it also has int plus. So these two could be possibilities. So those ones, we push them into the work list. And then we get int plus t, pop it out. And the same thing, we have t, leftmost non-terminal is t, so we have two ways to expand it. So we expand it either as int plus, we write this t as int, and we write this t either as plus e. Then we come and compare. So here we have int plus int, matches exactly our token int plus int. This one, int plus bracket, does not match, so of course that one would have to be pruned. Okay. So in this case, we push only int plus int into the working string. Then we have int, now we pop, previously of course, now we have int plus t plus e, so that's what happens, we pop that next. Then we write our leftmost non-terminal will be t, and we have the two options. When we write this t with the two options, then we compare our sentential form. We have int plus int plus, int plus int. There is no plus, it will never match, so that will not work. Then the same thing here, we have int plus, the token, terminal symbols end at the bracket. Here we have no bracket, so those two, we prune them and we cannot go ahead with them. So we are left with int plus int. Then this one, in fact, there's nothing to rewrite. So it's just a stream of a sentential form that only just has terminal symbols. We compare and we see actually there's a match. And we say we have found, we have managed to derive the structure starting from E up to int plus E. And now the sequence of productions that we have applied is what now form the parse tree. Okay, so with the leftmost BFS, we've had a substantial improvement over the naive algorithm. As you can see, we're able to prune the productions that will never lead to success. So we reduce that wasted effort. Also, by rewriting just the leftmost non-terminal, we reduce the branching factor, making it a much more efficient algorithm over the naive BFS. Yeah. So leftmost BFS is guaranteed to find a valid pass of the program if one exists, meaning there is the grammar, the program is syntactically correct. Leftmost BFS is guaranteed to find that parse tree. It can also be modified to find if a program can't be parsed, but that's out of the scope of what we're doing. But we're still not out of the woods. There are still some problems that we're going to see. So for example, look at this grammar. What do you notice about this grammar? So you can see we have one non-terminal A, and every time we rewrite the non-terminal, we rewrite it with itself. So there's recursion that is happening, right? So A is written as A or A. A is written as A or B. So anytime you want to rewrite this part, you rewrite it with A itself. Yeah. So you call A and rewrite it. So you keep always generating an A. So the only way to delete the non-terminal is to use this production. Okay. And this is a good grammar. It works, but we'll see that it poses a challenge when we start using leftmost BFS. So let's assume that that is the input string that we're getting for this grammar. So using leftmost BFS, as we've done, let's try and do it. So of course, we start with the grammar start symbol, which is A. Then we rewrite A. We have two options. The leftmost non-terminal is 1. So we have the two options to rewrite A. Sorry, 3 options. So we have AA, AB, or C. Then we prune. When we compare, this is a terminal symbol. It does not match what we have. So of course, we prune that. So we are left with AA and AB. So we push those into the working string. Okay. Then we come and then get the top. The first one of the work list will be AA. So now what do you notice here? These two working streams that we push into the worklist, the leftmost non-terminal is the same. They just are repeating the same thing. So there's almost no way to distinguish between the two because it's both an A and an A. So, but let's see. So if we take AA, so what we're writing is this A. So we populate the options. So in this case, now we have AA, or if we write A using AB, we get ABA. If we write this A with C, we get CA. Again, we do the match. We prune that because it doesn't match. Our terminal symbols. So we are left with these two guys. So we push them into the working stream. Again, you notice the leftmost non-terminal is still the same for all options that we have. So I hope you begin to see the challenge that we are facing. So we pop off, the next one will be AB. Again, so we have just A. We do the breath first. We write the leftmost non-terminal in this case. And so we write the leftmost non-terminal. Where's the zone to join? Okay. Again, we do the pruning. We're left with AAB, ABB, right? So we add them. So you begin to see that we might never terminate, or rather, by the time we generate a string that has all this, we'll have wasted a lot of time. Okay. And nothing is changing. Our leftmost non-terminal remains the same. Yeah. So each rewrite will just add another of the same that has exactly the same non-terminal. Okay. So we're saying grammars such as this one that we have, where we have what is called left recursion, where the non-terminal that is being rewritten is being written with itself at the leftmost position of the production. So the repeating non-terminal is at the leftmost position in the production. So the meaning that for leftmost BFS, it will always be the same A that we're rewriting. So that becomes a challenge. So grammars like this can make parsing take exponential time. And it also uses exponential memory because you're going to keep expanding, and we're not even guaranteed that it might ever complete. So when you're doing leftmost BFS, then we have to make sure we eliminate these kind of grammars, and we'll be showing you how to hack the grammar to eliminate now what you've identified as left recursion, okay, in the grammar. So what if we search the graph with a different algorithm? Okay, so we've seen the naive breadth as such. We've seen its challenges. We've introduced the use of leftmost derivations and pruning by comparing the terminal, a prefix, ensuring we have a prefix in the rewrite rule and comparing that to the token stream from the scanner. But we've seen that even if that works a bit faster, there's still a challenge of if the grammar has left recursion. So let's look at another approach, which might be an improvement over DFS. And this is now doing a depth first search. Okay. So depth first, we go down one branch until the end, and then we backtrack if we don't find a solution. So this one uses a depth first search. The advantages over BFS is that it considers, first, it has a low memory usage for the reason that it considers only one branch at a time. So you're not loading everything onto your memory as you try to keep track of the different options as we were seeing with the BFS. It has a higher performance on many grammars. It runs pretty quickly, and it is easy to implement. And we'll be seeing that you can implement it using a set of what you call mutually recursive functions, what is called recursive descent parsing. We'll be looking a bit more in detail. So let's look at how the leftmost BFS operates. So in this case, we said we're just going to go down one branch, and only when we don't find a match do we backtrack and try the other option for the particular non-terminal we are rewriting. So in this case, we have the same string. The token stream is int plus int. We start with the remember it's still a top-down parser, so we start with the start symbol for the grammar, which would be E. So in this case, E has two options. We have T or T plus E. So you take one branch. So in this case, we start with the one that's listed first. So we go with T. So we write E as T. And then for T, we're also doing a leftmost DFS. So we're going to write the leftmost non-terminal and go down its branch. So we come to T. So T, the options are either int or bracketed E. So in this case, we choose the branch for the first branch, which is int. And then we find that it cannot generate for us int plus int. So we backtrack. And then now we try the other option for T. So in this case, we're going to try bracketed E. Okay. Then the same thing, we find that we have a bracket. It's not going to match with our token string, so it doesn't match. So we backtrack. So now we've tried the first option of writing EST. So we backtrack again from that and try the other branch. So now we come and rewrite E as T plus E. Then again, leftmost, so we rewrite T. We have the first branch will be T as int. So we'll have int plus E. And then from here, we rewrite the leftmost. Is that a question or somebody trying to enter? Okay. So in this case, again, we rewrite the leftmost non-terminal. So here we have a match int plus. So we come and rewrite E. And we've chosen to write E as the first branch, which would be T. Then we write T as int. And we have a match, because now when we look at, we just have terminal symbols. You have int plus int, which matches int plus int. And we have a match. Okay? So you see that leftmost DFS, in this case, works much faster as opposed to generating a high branching factor. It's even much more condensed than leftmost BFS. But it also has challenges. The same thing where we have left recursion, where the leftmost non-terminal that we're writing a symbol from the grammar in the leftmost position of a derivation or in the production rule, like this. So A is written as A, starting the leftmost position is the non-terminal we're writing. So this is also problematic. As you can see in this case, if we write A, you're going to write it as AA. Then the leftmost non-terminal will be A. We take the depth first, meaning we take the first production, we write it as AA, and you get the drift. So if we're just trying to parse C, our depth as such will take us a very long way before we ever get to C. In fact, this will never terminate, because each time we have to rewrite AAA. So clearly, leftmost DFS also has challenges with left recursion. Okay. So a non-terminal, as I've said, a non-terminal A is said to be left recursive, if and only if we have be able to write A in a series of rewrites with the following format, where A comes at this leftmost position, and then we have omega, which is some string which could be made up of terminal, non-terminal symbols. So leftmost depth first such may fail on left recursive grammars, the same way we said that even for leftmost BFS, if there's left recursion, it is a problem. Fortunately, it is possible to eliminate left recursion for many grammars, and we'll be showing you how to check. If you have a left recursive grammar and you want to use these algorithms that rely on leftmost derivations, like left DFS or left BFS, then you'd have to eliminate the left recursion. Otherwise, your grammar, the parsing may never terminate. So in summary, we're saying that leftmost breadth search works on all grammars. Worst case runtime is exponential. We've seen it can take a very long time. The same thing with memory usage is not good. It is rarely used in practice. You will not find a self-respecting compiler that is based on leftmost BFS. For very simple programs, maybe like the ones you're implementing for your mini grammar, probably it could work if you eliminate the recursion if it's there, but it's rarely used in practice. Leftmost DFS has a restriction that it can only work on grammars that do not have left recursion. The runtime can also be exponential, especially if you don't fix your grammar, track it to optimize it for leftmost BFS. Memory usage is not as bad as leftmost BFS and can be used in a limited form as what is called recursive descent parsing. Yeah, well, you just define mutually recursive procedures for each non-terminal. So we'll be looking at that in detail. So now the other option, so we are still looking at top-down parsing. So you've seen the challenges of taking parsing as a search. We said you could either do a depth-first search or we can do a breadth-first search. And you've seen what the challenges are in terms of time taken, memory usage, challenges with the types of grammars that can be parsed, etc. So the other approach to top-down parsing is what we call predictive parsing. Okay, so let's look at predictive parsing. So you've seen that oops, where have I gone? Sorry, I think I have done the wrong thing. Let me slide all that. Okay. Yeah, so here. So leftmost DFS or BFS are backtracking algorithms because we're doing it as a search. You take one branch, if it doesn't work, backtrack to the last known match and try another option. So we are basically guessing which production to use. Then you backtrack if it doesn't work. We're basically trying to match the prefixes by luck. You know, there's almost no, I don't need to say intelligence, but we're just chancing. Do this, check if there's a match. If not, go back, try again. So there's nothing intelligent about that algorithm. So there's another class of parsing algorithms which are called predictive algorithms. And as the name suggests, we predict which production to use. We're not just going to guess. We predict which production to use and we totally avoid backtracking. And the production to use is predicted based on the input remaining to be parsed. Okay, that's it's called predictive parsing. Oh, goodness. Every time I use the arrow keys, they take me to the wrong place. Just have to remember to do this. Yeah. So we're saying based on the remaining input, we want to predict without backtracking which production we are going to use to parse. Now, as with anything, there are always trade-offs, okay? So predictive parsers work very fast, which is something we want for our compilers. However, they are weak in the sense that they cannot accept all grammars. You'd have to engineer your grammar so that it can work with predictive parsing, okay? So here the trade-off is basically between expressiveness for speed. Limited, like we said, the leftmost BFS can work for any grammar. Predictive parsers work for a restricted type of grammars, and we're going to be seeing what those grammars look like. So they're fast in the sense that the algorithms can run in linear time. And when we have what is called table-driven predictive parsing, it's even faster. And we'll be seeing how to come up with the table-driven parsers. But we said not all grammars can be accepted by predictive parsers. So if you want to use a predictive parser, you have to make sure that your grammar conforms to the properties of grammars that work with predictive parsing. So let's look at how predictive parsing works. In the previous slide here, the prediction is based on looking at the remaining input. So of course, at the beginning of the parsing, the remaining input is the entire program, okay? And you're going to now just start with the leftmost position. Because remember, we work from left to right. So you're going to look at what's coming next, and then you try and predict which production can be used to generate what is coming next. So we want to completely avoid backtracking. So how this is done, we exploit a look-ahead principle. And as the name suggests, you want to look ahead into the token list, a few number of characters, to then see what is coming up next, therefore what kind of production should we use. So the problem here is to ask, given, of course, we're starting with the start symbol because we're doing top-down parsing, How do you know which productions to use to get to the input program? So we look at, we decide which production to use by looking at some number of tokens. It could be 1, it could be 2, it could be 3, etc. There are different number of look-ahead tokens. And when you look at those look-ahead tokens, then you compare, you look at which productions can produce them. And then you choose the one that is guaranteed to produce the look-ahead tokens that you have taken into consideration. So let's see how we implement predictive parsing. So it's only possible if we can predict which production to use given some number of look-ahead tokens. And as I said, the number of look-ahead tokens varies. Some can just use 1 look-ahead token. Others can use 2, 3, or more, right? Now, if you increase the number of look-ahead tokens, it increases the type of grammars we can parse. Remember, we said already predictive parsing is restrictive in terms of the types of grammars. But increasing the look-ahead tokens slightly increases the number of the type of grammars that can be parsed with predictive parsing. On the converse, if you decrease the number of look-ahead tokens, you decrease the number of grammars that we can parse, but it simplifies the parser. It makes the parser easier to implement. The fewer the number of look-ahead tokens, the less complex it is to implement the algorithm. The more the look-ahead tokens, the wider the range of grammars you can parse, but the compiler, the parser implementation is more complicated. So we're going to look at an example of how predictive parsing works in general, and then we'll focus on predictive parsing that uses just 1 token of look-ahead so that we keep it simple for purposes of understanding parsing and even to guide you as you do your next task. So predictive parsing, so we have the same grammar. Now this is our token using from the scanner. So we are saying we can use either 1 or 2 or 3 tokens of look-ahead. So I want to just explain how that works. And we said to be able to know what to do next, to decide which production to use, you look at a number of look-ahead tokens. So of course, we start with our grammar start symbol, which is E, because it's still a top-down parser. And now what we want to do is to look at the remaining tokens. Based on the look ahead, we look at either 1 or 2 or 3 or however many we decide to figure out which production for E, between now E is written as T or E is written as T plus E, can give us the look ahead tokens that we use. So for example, if we decide to use 2 tokens of look ahead, we're going to look at the next 2 tokens in our input and it's going to give us int plus. Of course, now when you look at the options for E, which production can give us int plus? Definitely not E goes to T. We would have to choose E goes to T plus E because we are seeing there must be a plus. Okay, so we're able to predict the production to use by looking at what is ahead of us. So in that case, we choose T plus E. Then, if you want to now rewrite T, we have 2 options. We have an option of either int or with a bracket. So we can decide to now look at some look-ahead tokens. So we can decide, let's use 1 token of, supposing we're using 1 look-ahead token. Then, of course, you're going to choose T goes to int because you cannot choose T goes to bracket because we don't have a bracket here, we have an int. So then we'll choose T goes to, we write this T as int. Then now we have the working list now has E. So in this case, we have a match. Okay, so we've matched int plus with int plus. So now we're going to the remaining part of the token list that hasn't been matched now is from the bracket. Okay, so we're now going to look at look ahead tokens from this bracket to help us determine which production to rewrite for E. So supposing we use 1 token of look ahead to help us determine between the 2 productions for E. So here, of course, you have to sort of figure out that E, we need a way that we get a bracket. So we decide to rewrite it as T because T can give us a bracket. And then T, of course, we're going to choose T goes to bracket E. Okay, so it gives us int goes to bracket E. And you get the gist now. So right here, we've now find that we have matched. We now have int plus open bracket, int plus open bracket. Then we now need to figure out how to rewrite E. So we now, our remaining input is what is in light gray. So we decide now the look ahead tokens. So in this case, supposing we use 2 look ahead tokens, then of course it's going to help us to predict that we should use this production as opposed to E goes to T. So we rewrite this E as E goes to T plus E because we've seen there is a plus. Okay. Then we now want to rewrite T. The remaining input is still int plus E because we've not yet done a match. We use the one look ahead token. We have the int. So we choose the production that goes to, gives us an int. We can't choose the one that gives us a bracket. So we write it with T goes to int. And then we have plus and E. Now in this case, we have a long token string that we can match. And in this case, now we are saying that we are able to match up to here. So we have int plus open bracket int plus. So we now, the remaining input, the remaining token input is int right closing bracket. We want to now make a decision between the 2 productions for E. So that's the remaining input. So we choose T goes to int. If we want to look ahead token, we write T as int because we can't rewrite T again with an open bracket because we don't have an open bracket. We just have an int. And we finally have matched the whole input. Okay. So that's how predictive parsing works, that we take advantage of we have a look ahead token. It could be 1, it could be 2, it could be 3. But the look ahead tokens, once we compare them with each production for the non-terminal we're writing next, can yield that particular terminal stream. And then we are able to make that choice. So unlike in the BFS or the DFS where we just did not know, we had to generate any by guessing tests. If it doesn't work, backtrack, try the other one. Here we do not want to backtrack. And of course, you can imagine backtracking increases the complexity in terms of the time. So if we can avoid backtracking, the better. And actually, you find that most parsers would be, if they're top down, they would be using predictive parsing because it gives you a much faster way to parse. So I hope we are all together. So we carry on.
Yes.
Thank you. So we've said the number of look ahead tokens determines a lot. If we have a big number for the look ahead tokens, we increase the scope of grammars that can be parsed using predictive parsing, but we complicate the implementation of the parser. If we reduce the look ahead tokens, for instance, you say 1 look ahead token, then you have a very small set of grammars that can be parsed using one predictive parsing with 1 token of look ahead, but it makes the parser much easier to implement. Yeah. So as I said, we're going to focus on LL1. I'll be explaining what this means. So we're looking at 1 token of look ahead. So this is an example of a simple predictive parser. It's called an LL1 parser, where the first L means we're scanning our tokens from the leftmost to the rightmost, as usual. And the second L means we're also doing a leftmost derivation. So whenever we have a production that has more than 1 non-terminal, we rewrite the leftmost non-terminal. And then we have 1 token of look ahead. So when you hear a predictive parser called LL1, that's what it means, left to right, leftmost, and 1 token of look ahead. So we want to construct a leftmost derivation for the sequence of remaining tokens. So whenever we are now going to expand an terminal, we're going to predict the production to use by looking at the next character in the input, the next token in our input. and the decision is first, you just choose the production that can generate that next character. So easy to implement, but restrictive in terms of the types of grammars it can work with. Oh gosh, and I've done the same thing. Okay. Now, we've said that you can have table-driven parsing, which makes it even faster. So I want us to look through how we implement what are called LL1 parse tables. Okay. So we start with a grammar. Remember, now we want to create a LL1 parsing table that we now use to do parsing. And we say that table-driven parsers are much faster to execute and easy to implement even as code. And I suggest that most of you will either implement LL1 parsing or probably recursive descent parsing. Yeah. So I want you to follow what we're going to do in terms of constructing the parse tables, because after this, I will now start asking you to start implementing your parsers. Okay. Where to still evaluate your scanners. Last week I got pulled into a meeting with the chancellor. Even today, the same thing. It's looking like my Thursdays are a bit shifty, but we're going to look for time where we're able to do the assessments with good, so that we finish with the scanner assessments, and then we will focus now on the parsing, implementing your parsers. So we start with a grammar. In this case, we have two non-terminals. We have E and op, and we have 5 terminal symbols. We have int, we have the open bracket, we have the close bracket, we have the plus and the times. So what we want to do is construct what are called LL1 parse tables that implement the simple LL1 predictive parser. So the parse table looks like that. We have a row for every non-terminal in the grammar, and we have a column for every terminal in the grammar. So in this case, we have two non-terminals, E and op. So we have a row for E, we have a row for op. We have 5 non-terminals, the ones that are in blue, and we create a column for each of those terminal symbols. So we have our table, it will be M by N, where M is the number of unique non-terminals, and N will be the number of unique terminal symbols. Then now what we do is ask ourselves, if I was to rewrite, so of course this bit here, the columns are representing, remember we're doing one token of look ahead, and we're interested in tokens. So these are our terminal symbols. So we're saying we have the next character, the next token of look ahead can either be an int or a open bracket or a close bracket or a plus or a times, because it's the only thing that can come from the scanner. So then we're saying if I'm currently rewriting non-terminal E and the next token of look ahead is an int, then the production I should use is the one that has a right hand side as int, which would be this one. So this is the production we would use. If I'm trying to rewrite E and the next token of look ahead is an open bracket, then this would be the production to use, because it's on that would, this open paren is what would give me the open paren that I need. So this, you put the entry. So the table entries are the productions to use where this non-terminal is being rewritten and this is the next token of look ahead. So that's how to read the parse table. So let's do the one for op. So if the non-terminal to be written is op, and the next symbol is an int, it's undefined, which would mean it's an error, right? If you're expecting an operator and you get an int, then that is a syntax error. So anything that is undefined becomes an error. And now you see how easy it is not to give very good error messages, because here you'd be saying expected an operator, but got an integer, or something expected an operator. In this case, for instance, if you're writing an E and you get an open bracket, then you'd be saying expected either an int or an open bracket. So you begin to see how we're able to come up with meaningful error messages because we know what we expect. So predictive parsing in that sense makes it very easy to even give out very good messages. So for the non-terminal op, the only place which should be defined is, because the only productions we have is either opposition as a plus or operator is written as at times. So that's why we'll have the entry. So if you're writing op and the next token of look ahead is a plus, then you're going to use this production. So that's the one we put inside here. Or if you're writing an op and the next token of look ahead is a times symbol or the multiplication, then that is a production to use. Have we understood how to come up or how to read a past table?
Yes.
Okay. Thank you, Craig and Hansel and everybody else. So let's look at an example now of LL1 parsing. So we have our grammar, we have the token list from the scanner, and we have constructed a parse table. So how does LL1 parsing now work? How do we use the parse table to determine whether the token stream from the scanner is syntactically correct? So we're going to have two stacks. So we have the stack that has our work list as before, and then we have the stack that has the remaining input. So we are going to load our input from the scanner. So the first thing we do is we introduce a special symbol, which is what we call the end of character, end of input symbol. So you've seen we put this $sign here, and you put it on both sides. We'll be seeing why it's important to do that. And we're saying that this $sign, this symbol is the end of input marker, and the parser uses it to know that we have consumed the entire token list. Yeah, by the time the parser is processing that, it means you have successfully gone through the entire token list. So this is a way for us to know that we've consumed the entire string. Okay, so that's the first thing that we do. Now in this case, you see I have changed how I have written how we have filled out the parse table. So in the previous example, we were writing the productions themselves inside the parse table. Like you write int, you write op. But what makes life easier is we number our productions. So we have a numbering sequence, 1, 2, 3, 4 for our 4 productions. And so what now we are doing with the parse table, we are writing the production number inside the parse table. So this means that if you're writing non-terminal E and the next token of look ahead is int, then you're going to use production 1. If you're writing non-terminal E, the next look ahead token is an opening bracket, you're going to rewrite it with production 2. You're going to expand it with production 2. So you just write the production numbers as opposed to the actual production. So as you can imagine, for some grammars, the production will be very long. So you don't want to have to squeeze a lot of stuff inside your table. So just create numbers for each of the productions. Each production should have a unique number. Then we fill in the numbers instead in our table. So we put in our end of input symbol, then now we start parsing. Okay. So how does predictive parsing work? So, sorry, also forgot to mention here, of course, we always start with the start symbol of the grammar. Before we start anything, we load the start symbol in the working list on this side, and we've loaded the entire token stream on the other stack. Now, predictive parsing has 2 steps. There's what is called the predict step and the match step. So I'll start with the predict step. So whenever the first symbol in our work list is, I remember we're doing leftmost. So if the leftmost non-terminal to be written is, if the leftmost symbol to be written is a non-terminal, then we're basically going to look at the parse table to check which production to use for this non-terminal, where the next token of look ahead is the leftmost, is the leftmost symbol on the token input. So in this case, we're going to be asking if I want to write E and the next look ahead token is an opening bracket, which production should I use? Then you just come and read from here and you say, aha, I'll use production 2. Okay, so that is the predict step. So we're going to use production 2, and then we rewrite now our E with production 2. So in this case, now we write E as bracket, E op E, close bracket. Of course, the end of input symbol remains there. Then, now we do the match step, the next step. So the next leftmost The first symbol now in our work list, what we are guessing, is a terminal symbol because it's an open bracket. So whenever we have now the open bracket, we do a match step. So we're going to ask, does this match what is on the top of the token stack? Yeah, so we match it against the first symbol of the string that is being passed. If they match, we just consume them. So basically you get rid of them, you pop them from your stack. So that bracket has matched, this bracket has matched this bracket. So now we come to the next stage. Leftmost non-terminal is an leftmost symbol in the work list is a non-terminal. So we do a predict step. So you're going to check E when the look ahead is an int, and it's going to tell us it's production 1. So we write E with production 1. So int just becomes int of E. Then the next step, we have a terminal symbol. We do the match step. So int and int match. So we get rid of them, we pop them. Then we have a non-terminal. So we do a predict step op when we have a look ahead of plus. That tells us we write op with production 3. Then we have that. We write it as plus. Then now we have match step because we have 2 terminal symbols. We compare them, they match, we pop. Leftmost non-terminal, we do a predict step. E, when we have an open bracket, use the second production. When we have the second production, we write E as with the second production, which would be now E of E. Then again, now the top of our work list stack has a terminal symbol. So we do a match step, bracket, bracket, match. We put them. Leftmost non-terminal is an E given int. We write production 1, int of E. And then on this side we have int. So we do a match step for this int. And we're matching it with this int. They match, so we pop. Then we're left with op. So op, this is a predict step. We predict which production to use if we're writing op, and the next look ahead token is a times. So we come read our table op, look ahead is times. It tells us to use production 4. So we write op with times, and then again we do the same thing with E given int, production 1. We have int. Match step, int and int match, another match step, bracket, bracket, match, another bracket, bracket, match, and finally, end of input on this side matches end of input. So unless these two match, that you're matching end of input with end of input, it means you have consumed the entire input and you have had a match. You have successfully found a pass. So if we didn't have this, we would not know whether because we could finish on this side, but there's a token that is not yet passed, or vice versa, which would be grammatical and ungrammatical. So it helps to put this because then if they match at the same time, then we know we've looked at the entire input and we have a successful pass. So that is how a top-down LL1 predictive parser works. We have the pass table. We've shown you how to create a pass table. And we've also showed you how to use the pass table in the algorithm. So we have the predict step, we have the match step. The predict step kicks in if the symbol in the work list that we are matching is a non-terminal. So then we predict which production to use by looking at the look ahead token and rewriting. If it is the work list at the top of the stack has a terminal symbol, then we do the match step. If they match, we pop them and then we continue with the leftmost non-terminal. So let's look at an example of error detection. So that was an example of success. So in this case, we have the same grammar, we have the pass table, and we have int plus int. So of course, we can see this would not work because our expressions require brackets as per the grammar. You either just have a single integer, or if it's an operator, there must be the brackets. Okay, so we expect this to be error, to detect an error. So as before, we load our grammar start symbol and put the end of input on both sides of the stack. We do the predict step, int with a e with an int is production 1. So we write e with int. Then we do a match step, int and int match. Then in this case, we find an end of input on the work list, but on this side, we don't have an end of input. So it means that clearly this is not grammatical. There's something that is wrong with the way the grammar has been written. And so that one, we just flag an error. Yeah, so that one we report an error. Another case for an error report would be as shown. So here we can see what is missing. As long as we have brackets, as per our grammar, we require an operator, but our token stream from the scanner does not have an operator. So again, we load onto the worklist stack, the grammar start symbol, and the end of input on both sides. We do the predict step, e open bracket, write to production 2. Then we do a match step because both of them have a terminal symbol, bracket, bracket, they match, so we pop e to the predict step, e with an int, use production 1. We write it as int. Again, 2 terminal symbols, we do the match step, they match. Non-terminal op with open bracket. So here you notice, so here, the operator with open bracket is undefined, meaning that we do not expect to see, whenever we see an operator, whenever we are writing an operator, we should not get an opening bracket. Yeah, so this now just gives us syntax error. Expected operator found opening bracket instead, or something like that. Yeah, and so we flag that as an error message. Okay. So in summary, we've looked at the LL1 algorithm using an example, but this is the formal definition of that LL1 algorithm. And now this is what you need to focus on because you will soon be using it to implement your parsers. Okay. So supposing a grammar has a start symbol S and we have an LL1 parsing table T. We want to parse the string omega. So we have the start symbol is known and we have populated our parse table. And we're calling our parse table T. So the first thing we're going to do is initialize a stack containing the start symbol and the end of input file. These will be the 2 things in the stack. Then we enter a repeat loop. So while the stack is not empty, or repeat until the stack is empty, you read the next character from omega and we let that character be T. So T is our token, 1 look ahead token. If the top of the stack is a terminal, what are we doing? We're doing the match step. Okay, so we match. If the top of the stack R and the next look ahead token T do not match, we report an error. Else, if they match, you consume the character T from the input and you pop the terminal symbol R from the stack. If the top of the stack is a non-terminal, A, now here I want to do the predict step. So we check if in the parsing table, the entry A, T, meaning the row with non-terminal A and the column with terminal T is undefined, report an error, like the example we've just seen before this slide. Else, if it is defined, you replace the top of the stack with the production, that is the entry of T, A, T. Okay. And really that is how to implement the LL1 predictive parser. Fairly straightforward. If you have the parsing table, then it becomes easy to parse using this. So let's look at a simple LL1 grammar. And this could now be the kind of mini grammars that you have for your languages. So we'll be seeing actually what is meant by an LL1 grammar is that with one token of look ahead, you should be able to uniquely or confidently select a production. Yeah, so like in this case, if you see an if or a while or 0 question mark not plus plus minus ID constant, it is clear which production to use. So there's no ambiguity. Okay, and that's why we're saying that the grammars are restricted, because it may not be the case that you can have a grammar that's just one token of look ahead is able to distinguish between all the productions in the grammar. Okay, and that's why we said if we have more look ahead tokens, then it means we have more variety in terms of the grammars. They can be more complex, but then the parser becomes more complicated. So let's look at this as an example of an LL1 grammar. So what do you notice about this? How many non-terminals do we have?
3.
Okay, and then we have pretty many terminal symbols. So what we want to do is construct a parse table for this grammar. I've done the same thing. I keep doing it. I don't know what I'm going to do to stop doing that. Yeah, we were here. So this is an example of an LL1 grammar, and these are examples of statements or fragments of source code that a programmer can use right based on this grammar. So you can say ID, arrow ID, well, not 0 ID, do, decrement ID, etc. So what we want to do is show how to implement a top-down parser for this, a predictive parser for this. So the first thing is to construct the LL1 parse tables. And this is now what you guys are going to be doing. If your group chooses to use to implement a top-down predictive parser, this is what you're going to do. Okay. So the first thing, we have our grammar. We label all our productions with a unique number. So in this case, statement has 3 productions. Expression has 5, 1, 2, 3, 4, 5. And term has 2. So in total, we have 10 unique productions. So each of them, we give it a number. Then we said our rows in our parse table will have a row for every non-terminal. So we have a row for statement, for expression, and for term. And then we have columns for all our terminal symbols. So in this case, all of them, if, then, while, do, arrow, ID, 0 question mark, not, plus plus, minus minus, again constant. So now what we want to do is construct the LL1 parse tables. So of course we're going to start with the simplest productions. And what do I mean by simple? Where we're not having any recursion or a production that doesn't call another non-terminal. Yeah, so like in this case, term, these ones are pretty easy because term just goes to a terminal symbol. So we expect an entry for term and ID to have 9, isn't it? So we look at that. So term, look ahead token ID, we have production 9. If you're writing term and the look ahead token is a constant, we're going to use production 10. So we put in those 2 entries in the parse table. So we have 9 and 10 in the correct column. Then now we can do expression. So expression plus plus. So these ones are pretty easy because they're all starting with a token, a non-terminal. We have a prefix which is a terminal, sorry. So expression, if you start with 0, use production 5. Expression, if it starts with not, use production 6 and all that. So for those, we put in those productions. So 5, 6, 7, 8 are fairly straightforward because the productions start with terminal symbols. So now let's see what happens when the production starts with a non-terminal symbol in this case. So for instance, expression is written as term arrow ID. And remember, we'll be writing the leftmost non-terminal. So now it has to kind of look ahead into this non-terminal and find out how would this non-terminal be rewritten. And of course, it would be written as either ID or constant if you're writing it as a terminal prefix. So then that means that if you know you're kind of looking through this term to see what it can become. So if you find expression and the next look ahead token is an ID, then it means you must use production for, because you can write now term to give you an ID. The same thing, if you're currently looking at, you want to write expression, and the next thing you're seeing is a constant, then you'd have production for. I hope you've gotten that. So now the entries we have is that for non-terminal expression, if the next look ahead token is an ID, then you use production for, because you know that now production for, you will rewrite it using this and it will give you the ID, the constant. Yeah? So we're done. Then now we go to statement. So 1 and 2 are straightforward because they all start with a terminal prefix if and terminal prefix while. So we easily do that. So if you're writing statement and the next look ahead token is an if, use production 1. If you're writing statement and the next look ahead token is while, use production 2. So you've put in those two entries for the statement row. Now we need to deal with this one. So I want somebody to tell us what entries do we put in. If you've understood what you've done for expression, what are the entries we put in for statement and expression?
I think you need to go to 4. If you read a statement for your parse table, you'll match it to the value for which statement follows expression. So that's probably the rules that begin from 4.
Yeah, so I need an entry. So I want the entries for statement. I want the entries that come in here.
So I think for ID, you'd have to do statement ID 4.
Why 4?
Sorry, statement 0 4, because I'm doing for 0 because 0 is a leading
So you're doing
terminal.
this one.
Yeah, for the second one. The first one, I'm not sure.
Okay. So what should the entry be in the table for 0 and statement?
For statement on the first row, under the 0 column, I would put number 5.
Number 5 or number 3? Because remember, the only way you can rewrite statement is either this production or production 2 or production 3. Yeah. So if we want to write statement and the next look ahead is 0 plus, so sorry, 0 question mark, then we must, the only production for statement that can give us a 0 is this one for expression. Because you know now once we have expression and we rewrite it, it will give us 0. Entry here would be statement 0, 3. That's a production you can use. The only productions for statement are these 3. You followed? The same way when we did expression and term and ID, here for term, we said for expression to rewrite as term, we look through term and we see term can be written either as ID or constant. So it means that if I have an ID or a constant and I'm writing expression, then this is the production that can give me ID or constant, because term can give me ID or constant. So the same thing for statement. If I have ID or constant, when I want to write statement, then I have to use, out of the 3 productions for statement, the only one that can give me ID is expression. Okay, so would be writing it, would be looking through like that. You take expression can be written as term or 0 plus, not blah blah blah. So if you start with the ones that are already this, then we don't know wherever we have a 0 or not or a plus plus or whatever, then the production that can give us that is expression. So we are going to have entries of number 3. But if you're rewriting statements and you see a 0, out of the 3 productions for rewriting statement, you can only choose expression. That is only you can ever get a 0 from statement. All right. And then you look through again, expression, look through term, term to come to ID and constant. The same thing if you have your rewriting statement and you have an ID and constant, then you'd have to rewrite it as expression so that you write expression as ID and constant. So if you have constant when you're writing statement, then you're going to use production 3. Have you followed that?
Yeah.
And that now becomes our parse table. Okay. So right now we are doing this parse table manually. But is there an algorithm we can use for constructing LL1 parse tables? Because you can imagine you have a very, very, like in the real world, if you have a very complex grammar, like a CFG for Python or for whatever language, it might not be feasible to come up with the parse tables by hand. So of course, for your simple grammars, you could come up with the parse tables by hand, but there is an algorithm that we can actually use to do it rigorously, and then this can be implemented as code. And of course, the intuition here, if you've understood how we've done the filling of the table entries, is to say that the next character, when we're doing, of course, that one token of look ahead, should uniquely identify a production. So we should pick a production that ultimately starts with that character. Yeah. So as we're saying, if I want an if, I had better choose. If I want to generate, if the next token is an if, I might as well choose the production that starts with an if. Okay, and that's the production you choose to rewrite. So it's straightforward. So the table, parsing table entry, where we're writing A with for this particular token, should be a production such that A is written as omega if and only if omega derives something starting with T. So we're basically saying there'll be an entry in the table for A, comma T, where T is the token of look ahead, and that production, that entry will be the production from the grammar that looks like this. A is written as some working string, only if the prefix, the first symbol of omega, can give us T. Yeah, and this is how we specify that more rigorously. But what is important is that you've understood what we are trying to say. So we'll stop there for today. So what I want you to do, whether or not you're going to use, you're going to implement a predictive parser or a recursive descent parser, which you're going to look at soon, you to create LL1 parse tables for your grammars. So of course, if you find that your grammar is not of this form, then we're going to wait until when we figure out, you'd have to fix your grammar. Yeah. So ideally, what you're going to now look is first answer the question, can our mini grammar be implemented? Can we implement a predictive LL1 parser for our mini grammar as defined? In other words, you're going to look at all your productions and confirm that what we've just said here, there must be the next character the next token should uniquely identify a production. So meaning that all your productions should be uniquely identified by a token of look ahead. Okay. So you're gonna go look through that, and if you find that the way your productions are, it is easy to identify a production just by one terminal symbol, then you come up with a pass table for your mini grammar. So something like this. So we'll see all your non-terminals on this side on the rows, and then your terminal symbols as columns, and then the entries of your productions. So that will be what you start working on now. From next week, I'll expect that you start implementing your parsers. So we need to have a makeup lecture so that we finish on the other algorithms that allow us to implement this. Then I'll communicate. So are there any questions? Yes, Edith.
I wanted to ask about the then and do.
You want to ask about?
The then and do and terminals. Would they also be written in the past tree?
I
In
can't
the
hear.
statement?
There's a bit of background noise. Could you ask your question again?
I wanted to ask what would happen to the then and do non-terminals
With
in
the
the
what?
past tree.
What would happen with
Then
what?
and do.
Could you just type your question because I'm not hearing you?
I have typed it.
Okay, so you're asking, like in this past table where we don't have, like now, if we're writing statement and we get then, is that what you're asking? What's going to happen?
Yes.
Yeah, it should just give an error because you cannot have a statement that starts with then. A statement as per grammar must always start with a terminal if. So if you're finding then it is a syntactic error and the parser should give an error message. And that's the example we saw somewhere around, let me see, it was somewhere here. Yeah, in fact, it was this one, where there was no, I think it was the next one. You see, like in this case, let me just go through this. We had to, then we had E. So here, we're expecting to write an op, and the next terminal that we're getting is an open bracket. But there's no entry for open bracket. So this just becomes an error message. Yeah, so the error message would be expected an operator, but got an illegal symbol open bracket. Is that clear, Edith? Okay, thank you. All right, so carry on. So look through your grammars. Check whether, in fact, your grammars are amenable to LL1 parsing. So it will be one of the options you'll have, either to implement a predictive LL1 parser or a recursive descent parser. I will not encourage you to implement bottom-up puzzles. They're pretty hard to implement. We're going to go through them to understand how they work. But for a school project, I would discourage implementing a bottom-up puzzle because of the complexity. So I want you to read up on recursive descent puzzles and also, again, on what you've done on LL1 parsing and start thinking through as a group which approach you will use for building your puzzles. So I will communicate through your class reps when we're going to have the next makeup class. I was hoping it was tomorrow, but I see like you have lectures in the morning. So we'll communicate for some time early next week. So have a good evening.
Good evening to you.
Thank you.